Okay, next we're going to further look at conduction velocities of axons. When we're talking about conduction velocity, we're talking about how quickly a signal can go down an axon. It's going to be much faster if you have myelin. It's also going to be faster if you have an axon diameter that's larger. So if we combine these things, we can note that if you had an axon diameter that was large and you had myelin sheath, then the conduction velocity down the axon of an action potential will be much faster than if you had a small axon diameter and no myelin. So keep that in mind as we move forward and look more at impulse propagation and how these signals are created. So next we're going to look at neuron structural classification. We want to look at this further before we continue talking about conduction velocity, mainly because we want to have an idea about the types of neurons possible in that talk. So structurally, there are 3 types of neurons, and it's just based on the number of processes extending from their cell body. So when we're talking about structural classification for a neuron, we are truly looking at what it looks like, its structure. For multipolar neurons, there are 3 or more things coming off the cell body. We call those things processes. So usually that's one axon and many dendrites. This is the most common type of neuron. Then you have bipolar neurons that have 2 processes, usually one axon and one dendrite. These are usually in the special senses, like the retina of the eye. Then unipolar neurons, which are sometimes called pseudo-unipolar, but they have only a single short process. But the axon does very quickly divide into a proximal and distal branch, sometimes a receptive or peripheral process, depending on where we're seeing this unipolar neuron. Many unipolar neurons are actually sensory neurons as well. So here we can see all 3 types of neurons. Multipolar neurons on the left, with its cell body, many dendrites, and one axon. Bipolar neurons in the middle, with its central cell body and only 2 processes, one being the receptive dendrite end, and the other being the conductive axon end. Then we have our unipolar or pseudo-unipolar neuron, with its cell body and one process coming off of that very quickly splits into a central and peripheral process. The central process generally goes towards the central nervous system, and the peripheral process generally goes to the peripheral nervous system. But there's modifications to these neurons. So the only thing that stays the same when we're talking about the structural classification of neurons is multipolar has 3 or more processes, bipolar has 2 processes, and unipolar has 1. Multipolar neurons, again, are the most abundant type of neuron in the body. They're the major neuron type, especially for the central nervous system, whereas bipolar is very rare and found in things like the retina of the eye or other special sensory organs like that of the ear or olfactory mucosa. And then you mainly find unipolar in the peripheral nervous system, and we're going to see that even though you can find it in the central nervous system, it's common only in the dorsal root ganglia of the spinal cord, which are neurons that are going to innervate the spinal cord from the back. And you can also find them in the sensory ganglia, or kind of bundles of cell bodies near cranial nerve connections to the spinal cord, specifically kind of at the adjacent area of the brainstem. So again, when we're looking at structural classes of neurons, we're looking at how many things come off the neuron. But you're starting to see that there's some information that is functional that is provided as we talk about that structural classification. Multipolar neurons are usually motor. They're common in the central nervous system, so if they're not motor neurons, they might be interneurons, which are the integrators for the central nervous system. Bipolar neurons are very sensory and usually very rare because they're only for special sense receptors. And unipolar are also usually sensory. So as we move on away from the structural classification of neurons, let's talk again about the functional classification of neurons. We've actually already talked about it. We may not have called it the functional classification of neurons, but we did talk about 3 overlapping functions for the nervous system, and the functional classification of neurons matches up to that. We had sensory input, and that information was carried by sensory or afferent neurons. We had integration or association, which is processed by central nervous system interneurons. And we had motor output, which is carried by motor neurons, sometimes called efferent neurons. Afferent signals are always sensory because they arrive at the central nervous system. Efferent signals are always motor because they exit the central nervous system and go to effector organs. And then we commonly see both motor, sensory, and interneurons in the areas around the central nervous system and in the central nervous system because of the communication cell to cell. So we're going to stop there. Very short video, but it's because the next topic is really going to get into the physiology of the nervous system and look at neuronal transmission, and that's going to depend on basic principles of electricity. So I'll leave you with this quote, and it's from your textbook. The human body is electrically neutral. It has the same number of positive and negative charges. However, there are regions where one type predominates, making those regions positively or negatively charged. What we're looking at here is essentially local situations where we're not considering the entire human being. And in these local situations, we're mainly looking at plasma membranes as barriers that are separating these regions of charge. That's going to be our focus in the next video.